All right, guys, last two remaining topics. In this video, we're going to cover these and then start some of the questions remaining. So starting with number 3, learn some basic facts about complex zeros of polynomials. First of all, what's a complex zero? A complex zero is a zero that's a complex number. And a complex number has a form like this, a plus bi. So in other words, it's got this I portion, right? Where I is defined as the square root of -1. So, up to now, anytime we had a square root of a negative, we said it's not possible, right? And it's true. It's not possible to take a square root of a negative within the realm of real numbers. But then we introduce what are called imaginary numbers. And imaginary numbers is just that, an I. I stands for imaginary. It's a square root of -1. Anything that has an I term in it is a complex number. Now, sometimes you might have a real number, and you could still consider a real number a complex number technically, because if the b was 0, for instance, then you just be left with the a part, and that's the real value part, right? So that means that really complex numbers, and we denote the set of complex numbers with this kind of fancy looking C, that contains the set of, should write it like this, contains the set of real numbers. So real numbers is a subset of the complex numbers. And by the way, the quotients are rational numbers, which are just fractions, right? That's a subset of the real numbers. And integers, which we denote by this fancy z, those are a subset of the rational numbers. So it kind of works like that, where complex numbers is the biggest category. It includes all real numbers. So anyway, that's what it is. Now, what does the fundamental theorem of algebra say? Fundamental theorem of algebra, just by the name, okay, this is an important theorem. But really, I don't know. I'm not sure if it deserves the name fundamental theorem of algebra. It is a very important fact about polynomials. And it was proven by this really famous guy, Carl Friedrich Gauss. So super famous mathematician. He did some incredible things. Super genius guy. And he proved this, and the format originally was that every polynomial has at least one complex zero. Complex, I said or real because, remember, complex includes all the reals as well. So they might be real zeros or they might be complex. As long as the polynomial function is not constant. Constant just means it's a number, right? Like p of x equals to 5. 5 has no zeros in it. Okay, and so the degree is at least 1, yeah? And then the coefficients should be real or complex numbers. So under those circumstances, then you have at least one complex number. But, that's not actually the way that I remember the fundamental theorem of algebra. And if you look online, you search the fundamental theorem of algebra, sometimes this version will pop out, but sometimes the second one pops out. This is an equivalent statement. And, it kind of follows directly. If you were to take this first statement that every polynomial has at least one complex zero, as long as the degree is 1, well, you can always reduce the degree by dividing by one of its factors, right? So divide by x minus c, you're going to reduce the degree by 1. And so you end up with this fact that any polynomial of degree n has exactly n zeros. Now, to me, this is a case where it's a very intuitive fact. Like if I think of quadratics, I know they can be factored into two solutions, right? Quadratic meaning like an x squared. And sometimes you're going to get imaginary solutions, but you're still going to get two of them. Like if you even think about the quadratic formula, right? It's x equals to negative b plus or minus. That plus or minus gives you the two different solutions. And another fact we learned previously was that if you have a polynomial of degree n, well, it's got n minus 1 possible turnarounds, right? Turnaround meaning where it's going up, turns back to going down, up, down. So like, let's say I have a degree 5. That means I'm starting going up, say. I can turn around once, twice, 3, 4 times. Now, how many times could I possibly cross the x-axis? Well, at most 5 times, right? So 5 times for 5 zeros. Sometimes those crossbacks might happen like so that it doesn't cross again, but then that just means you're going to have complex zeros instead. Now, the theorem says also to consider the multiplicity of roots. That's because, let's say you have something like x to the 4th power, where your thing looks like just like this, right? And you've got that 0 as a root at 0. Well, that's actually a 0 of multiplicity 4, right? So it's really like four zeros in 1. So if you consider that, then this holds true. Any polynomial of degree n has exactly n zeros. Okay, so that's something I wouldn't necessarily memorize as much as think just conceptually, think just intuitively that would be the case, right? N degree is going to have n zeros, exactly. Okay, the last thing to learn today is about conjugate pairs, the conjugate pair theorem. And the conjugate pair theorem says if P is a polynomial with real coefficients this time, you know, I wouldn't really worry too much about whether the coefficients are real or complex, because we pretty much always deal with polynomials that have real coefficients in this class, right? In fact, I very rarely see polynomials that don't have real coefficients with complex coefficients. It's kind of rare. In fact, I feel like the polynomials that we deal with almost always have integer coefficients, even easier. So anyways, what does the conjugate pair theorem say? It says if a plus bi is a 0, then so is its conjugate, a minus bi. What's the difference from a plus bi and a minus bi? Well, the sign change, right? The sign change for that imaginary part. Note, by the way, that the conjugate of a minus bi is actually back to a plus bi, because if you switch the sign from negative to positive, then you get what you get. Oops, sorry. I have to turn off my notifications. Did I? Oh no, wrong one. This one. Okay. Yeah, so like I was saying, so if I have a minus bi, and I wanted the opposite of that, it would be a minus negative bi, which is a plus bi, right? So they're conjugates of each other. The cool thing about conjugates is if you multiply them together, it gets rid of the I part. Watch this. If I take a plus bi, multiplied by a minus bi, what is that? You have a difference of squares here, right? A plus something times a minus something. So that would be a squared minus bi squared, right? Well, what is that? A squared minus b squared I squared. If I was to just, multiply that thing out. And then what is I squared though? I squared is by definition -1, because the square root of I is -1. So that's a squared minus b squared times -1. Or in other words, a squared plus b squared. So check that out, guys. A plus bi times a minus bi. If you multiply that by its conjugate, you get a squared plus b squared. A beautiful fact. Now that might seem a little amorphous to you. It might seem a little abstract to you in your brain. So let's just bring it down real quick to a real number example. Okay, so a plus bi times a minus bi is equal to that. So let's say I have just 2 plus 3i. Well, its conjugate would be 2 minus 3i. So according to what I just proved, that's 2 squared plus 3 squared, which is 4 plus 9, right? Which is 13. So that's a cool fact for conjugates. We're going to use that fact later on. Okay, and then last part is the factorization theorem. So factorization theorem says if I have a polynomial, then I can write that thing out in terms of either linear factors or irreducible quadratics. Irreducible quadratics come from if you have complex roots. So all that's really saying is, let's say I have a polynomial p of x, I can write it as a bunch of linear factors like x minus a, x minus b, x minus c, blah, blah, blah. And maybe if I have complex roots, something with x squared plus, I don't know, ax plus b, where I already use a, so I should use something different. Let's say it's a1, b1, blah, blah, blah. Yeah. And then maybe you have some number out in the front. But some real number. But yeah, so I can write any polynomial in this format. Now I don't need cubes, because if I have a cubic, then at least one of the factors is going to be a regular linear factor, right? Okay, so that's a pretty powerful thing. It means I can factorize any polynomial down to only linear terms and maybe, if necessary, some quadratic terms. Okay, let's get started with the next 3 questions. We're going to do 5, 6, 7. And then in the last video, we'll work on the remaining questions. Okay, so number 5 says find the remaining zeros of the polynomial with real coefficients and a specified degree in zeros, and then write it in its factorized form. So this is really cool, guys. What's really cool is, look, I have a polynomial degree 3. That means it's going to have 3 zeros, right? Well, I'm given one of them is 2, another one is 3 plus i, and by the conjugate theorem, the missing one is going to be 3 minus i. So I've got all the zeros. And now that I have all the zeros, I can write it out in factorized form. Factorized form is going to be x minus 2. It's actually going to be this, guys. It's going to be x minus the first root, x minus the second root, x minus the third root. And in this case, these are the 3 roots, right? So it's going to be x minus 2, x minus 3 plus I, and x minus 3 minus I. Okay, now this would be an answer, except I don't like that it has i's in it. And sometimes you're asked to write it in, when it asks for factorized form, it really means without any i's in it. So all we have to do is just multiply these guys together, and we're gonna see that the i's magically disappear. So let's do that as side work right below. Okay, leave some space for the end result right there. And the side work is gonna be out here. I'm gonna do x minus 3 plus I times x minus 3 minus I. So foiling that out, first term, second term, first term leading terms, I got x squared. Then the outer terms, it's going to be negative x times 3 minus I. And then these outer terms, it's going to be negative x times 3 plus I. And I reversed the order of the x's, I guess. Oh, no, I didn't. No, I didn't. That's right. Okay, last term is minus, so it's going to be plus, right? And it's going to be 3 plus I times 3 minus I. Okay, I'm too excited to do this, so I'm going to go straight to this guy right here. Remember we said that's a squared plus b squared? So in this case, it would be 3 squared, which is 9, plus 1 squared, which is 1. So 9 plus 1 is 10. So beautiful. The i's are gone there. This guy, I'm going to carry through this x squared, right? And here, this thing, let's write it like this. That's negative 3x plus ix, right? This guy right here, that's negative 3x minus ix, see, or xi if you prefer. But check that out. I've got a positive ix and a negative ix. Those guys are gone. They cancel each other out. Leaving me with, then, this last beautiful thing, x squared minus 6x, because the two negative 3x's, right? Plus 10. So you see this is a quadratic term, right? And the solutions to this quadratic term are 3 plus I, 3 minus I. Just for this first time, I'm going to prove it to you using the quadratic form. This is not necessary work. This is just I want to show you how this actually plays out. So what would be the solutions for this quadratic expression here? It'll be negative b, which is 6, plus or minus the square root of b squared, 36, minus 4ac all over 2a, right? Okay, that is 6 plus or minus the square root of negative 4 over 2. And the square root of negative 4, that's 2 square root of negative 1. Right? Everything is divisible by 2, so it's 3 plus or minus 1 square root of negative 1. Or I don't need that 1 anymore because it's just 1, right? And what is square root of negative 1? It's I. So it's going to be equal to 3 plus or minus I. So I got 3 plus I, 3 minus I. And look, that matched up with the original roots that was supposed to be, right? It matches up with these guys right here. So, final answer here. I'm going to write the final answer in red. X minus 2 and x squared minus 6x plus 10. This is the factorized form of that original polynomial. Sweet. Sweet. Okay. Let's go on to the next one. Next one is actually even easier question than this last one. This one was a little longer, harder because I had to worry about those that 3 minus I term and multiply the whole thing out. This one's easier because it's just a regular I that's the 0. So watch what happens here, guys. Okay, so I've got 0, 1, 4. That's 0, 1, and I mean. Those are 3 of the zeros, but I have a degree 4. That means there should be one more, and the missing one is just negative I. Okay, so that means what is the factorized form? It's x minus 0, or just x minus 1, x minus I, and x minus negative I, which means it's x plus I. So let's simplify that slightly. X minus 0, of course, is just x minus 1. And now x minus I, x plus I, that's going to be x squared minus I squared, right? That's already a difference of squares. So that's x minus 1, and then I squared, of course, is negative 1. So x minus negative 1, x squared minus negative 1, I mean. So I've got x minus 1, and x squared plus 1. And that is already my factorized form. So sweet, easy. That was number 6 just now. All right, 5 and 6 down. And on to the last question for this video. And in the last video, we'll cover the last type of question. So I've got a degree 5 polynomial this time. I've got 1, 2, 3 given to me, but the missing ones are the conjugates, right? If I have negative I, then positive I is the other one. And if I have 1 minus 3i, 1 plus 3i is the other one. So those are 5 zeros now. I found all of them. Now I can go straight to factorized form. So I'm going to get x minus negative 2, x plus 2. I'm going to get x plus I and x minus I, right? Then I'm going to get x minus 1 plus 3i, x minus 1 minus 3i. So those are all my... I did it kind of in a little bit backwards order, but it's same thing. Okay, I'm going to... I just finished doing x minus I, x plus I, so I'm going to reduce that in one step right here. It's going to give me x plus 2 first. And then this thing becomes x squared plus 1, right? So now all I have to deal with is that guy over there. We'll do that in purple. And let's do some side work here. X minus 1 plus 3i. X minus 1 minus 3i. Okay, so we're going to FOIL this thing out. First terms, I get x squared. Outer terms, I'm going to get minus x 1 minus 3i. Inner terms, I'm going to get minus x 1 plus 3i. I read first the order just so it's easier for me to look at it. And last terms, I'm going to get the 1 plus 3i, 1 minus 3i. And you notice this is a positive because I have a negative times a negative, right? Okay, I'm going to do this last part first because it's too exciting. That's 1 squared plus 3 squared, right? Which happens to be 10 again. So we did that before. Last time we did it was actually, I think, 3 minus I, but result is still 10. Okay, this guy, x squared, carries over. And then now this term becomes negative x plus 3i x. Okay, I know I changed it from how I did last time. Last time I had the x before, but same thing. This is negative x minus 3ix. And again, these guys, this is always going to happen. These guys cancel each other out. Okay, leaving me with x squared minus 2x plus 10. So that's what goes here. X squared minus 2x plus 10. And that is the factorized form that we were looking for. So there it is. Nice. Beautiful. I've got linear terms and quadratic terms, and that's it. Never had to go to cubic, just like the theorem had said. All right, you guys, see ya in the next one.